Charles hadn't started.
Yeah, I'm live streaming. Yeah, I'm live streaming. Sorry, guys. I'm just trying to get this thing to close. There we go. Oh, come on. That's good enough. All right, gentlemen. So welcome. Hopefully you all had a wonderful holiday. Well, Easter Sunday, or, you're able to spend time with loved ones and, do what you needed to do. We are rapidly approaching the end. Congratulations. I don't remember the names. Let me see. I'm not even sure if they were there. It was such a blur. But we did have at least 2 honorees from this course. Let me see if I can pull up their names. Let me see how long that's going to take. I have them right. Where is it? Where is it? It's not here. It's not that one. I have to go. Ooh. Yes, this is it. And this is it. So it should be right here. Right. Here it is. All right. So I don't think the gentlemen are here right this second. I think I would have said something sooner, but the attendance is a little bit skewed. Let me get these gentlemen. Let's see. So I just made a payment. Okay, yo, you just got back. Like, come on, you got to chill with all this. Okay, let me let these gentlemen in. I don't think the honorees are here at this moment, but come on. I don't really want to close. I just wanted to hide. Let's just go full screen. I think that'll work too. Okay. So congratulations to Ethan Drakes and Darius Porter. These were the recipients of the Outstanding Achievement in Business Cal for this semester. They were like the top 2 ranking students, but there are others that were close, and they were like, no, you got to narrow the list down. So I had to just choose a couple, but there were others that were close as well. Man, what is going on? This thing is like not responding to my touch at all. Okay, there we go. Okay, let me check one more time. Okay, you guys are looking good. Why did I do that? There we go. Yeah, so that award ceremony was this past Thursday. So I know a good amount of students showed up. I usually have a packed house because I'll be teaching a lot of classes. I don't even be realizing it until like we have those events. But that was this past Thursday. So yeah, again, we're rapidly approaching the end of all of this, right? So this week we're going to wrap up all the new content. Today we're going to work on section 4.5, integration techniques with substitution, and then on Wednesday that'll be the last of the new content. I want to say our exam 2 should become available this Sunday. If this is the last of the new content, it should be this Sunday. I think that's how I'll schedule it. If it's not, it should be this Sunday because I don't think it's anything beyond this, right? So, we'll go through the content for this week. We're going to wrap up chapter 4 and then wrap up the last of the new material. We'll take exam 2. Unlimited attempts. Now, again, when we're taking these exams, I usually try to I devote the entire week to the exam, and I try to make myself available, right? So the recommendation is to go through the exam, do the best you can, and then you can ask me questions. Sometimes students, you can challenge a lot of that stuff that's there. If you feel like you can recover some points, or if you feel like you were close enough and like you didn't receive credit, we can challenge it, and I can give you credit on the back end. So then that's less of a a probability or less of a likelihood that you'd have to redo that assignment, right? If you're trying to improve your overall score, I would encourage you to prioritize your exams because they count for nearly like 80% of your overall grade. I had to look at the syllabus again to see how I have the grading rationale, but I know the bulk of it comes from the exams. I want to say that the last day of class, like the last day we're going to meet, is the last Wednesday in April. And then that first full week of May is the final exam week. The final exam is going to be like how we've done exams 1 and 2, where it's just going to be available on Pearson from that Sunday up until that Friday, right? So you'll have access to it for about 6 days, maybe more like 5.5 days. It'll be available for the entire week of the finals. Also, the hard deadline for all assignments is that Friday at the end of the week of finals, right? It's that first Friday, or that, that when you look at that first full week of May, that Friday is the hard deadline for everything, right? So again, if you are trying to improve your overall grade, I would encourage you to prioritize your exams. Once your exams are wherever you want them to be within the constraints, then next I would do the best I can with the quizzes. The quizzes and the homework are a lot of work for little points, right? So you're not going to see a huge jump in your grade and going back and doing those. Those are more so practice to kind of get you ready for the exams. But the bulk of your grade comes from the exams. I know I'm kind of preaching to the choir because you guys were here. I would encourage you to kind of like be in the waiting room, maybe like 5 minutes before the start of class, because as my goal is to start class right at 6. I know I haven't had the best track record, but that's essentially what I've been doing. So it's like the thing I had to realize was, push my image to YouTube, because that's what the holdup was a lot of times. So I realized I had to push that like 10 or 15 minutes before I let you guys in, or before any of you guys show up, just for it to work properly. Because if I wait, then I think with the excessive amount of students on there, it just disrupts the image being pushed, right? But it seems like it's working for right now. Okay. Let me check on Zoom. I usually wait for the 15-minute mark, but okay. Let me let him in. Awesome. And then mark him here. All right. Yeah. Yeah. As usual, feel free to unmute yourself if you have questions, comments, or concerns. Just unmute yourself and get my attention, and we can talk about it. And aside from that, I can't think of anything else. So we're going to go ahead and get into this content for today, get into the material. Again, we're rapidly approaching the end of chapter 4 in the semester. Chapter 4 on integration. And so today, our second to last topic is section 4.5, integration techniques. We're going to be looking at substitution. Okay. A few objectives here. We like to evaluate integrals using substitution and then solve applied problems involving integration by substitution. Okay. I think it's still going. I'll just kind of give it a moment. Yeah, there it is. Okay. So integration techniques on substitution. The following formulas provide a basis for an integration technique called substitution. Let me grab this guy. Remove this over Chrome. Okay. Oh no. Something just stopped. Uh-oh. Oh, I hope my image is still being pushed. Oh, no. Okay, I clicked the wrong thing. Okay. Whoo, I got nervous for a moment there. Okay. So the following formulas provide a basis for an integration technique called substitution, right? So if we're integrating some expression to the power of r du, like u to the power of r du, then that's going to be u to the r plus 1 over r plus 1 plus c, all right? Integral of e to the u is e to the u plus c, right? Because e is its own derivative. Let's see. Okay, let's keep going. So the integral of du by u is the natural log of the absolute value of u plus c. And if u is forced to be positive, then you don't need the absolute value. And generally speaking, we do assume that u is positive, right? So, these I feel like they just become, easier to kind of see and remember just through practice, right? So let's look at this example. For this, why doesn't that feel right? For some reason, dy. They just wanted us to take the derivative. That doesn't sound right. Okay. Oh, okay. Yeah, that's what I thought. Okay. Yeah. Okay, that's fine. So dy, right? So, basically just take the derivative, right? So if we find the derivative, it's going to be dy by dx, right? If we take the derivative of this guy, that's going to be 3x squared. And then we can essentially use algebra to isolate the dy. So if you move the dx to the other side, then dy is going to be 3x squared dx, right? The differential of y, okay? All right, so let's kind of go with this for now. And I think they have that here. Okay. So then for this u, find du. So let's do something similar here. So then du by dx, so the derivative of u with respect to x, the 2/3 comes down, right? Yeah, I think we're okay. X to the power of, you subtract 1 to the negative 1/3, right? And move the dx over. So then our du is going to be 3 times the cube root of x under 2 dx. Okay, it's the same thing, right? I just moved the negative x1. I wrote it as with a positive power. Okay, it's looking good. We're going to keep moving. So for this y, find dy, right? Okay, so same kind of deal. So dy by dx, the derivative of e is itself, e to the x squared, but then we got to say times the derivative of the power, which is going to be what, 2x in this case. So then dy is going to be, I'm going to write it as 2x e to the x squared dx. 2x, oh, okay. I mean, that's fine. So you'll see here, e to the x squared, a power raised to another power is really multiplication, right? So e to the power of x squared is the same as e to the power of 2x. Yeah, I think that's okay there, right? So I'm just gonna move it. But it's this, again, a power raised to another power, we multiply those two. So e to the power of x squared is the same as e to the power of 2x. Okay, that's fine. We're gonna leave that as an exercise right here. Okay, so now if we're using substitution, right? So then it looks like we can do a substitution here. For instance, we're gonna say let u be what? That x cubed plus 1. So then that means our du, right? So now we're applying the technique that we just invoked, right? Our du is going to be what? 3x squared dx, right? If we use the same technique that we just did in the previous couple of examples, we can find this du. Okay, notice we have our 3x squared dx right there, all right? And we got our u, so now we're poised to do our substitution. So when we go to do our substitution, we want to choose a u such that when we find du, those components are there as well. All right. So let's do the substitution. So then the original guy is going to become the integral of u to the power of 10 du. All right. Okay. So then that integral becomes what? U to the power 11 over 11 plus plus a constant, right? And then we need to put the substitution back. So then that's going to be 3x squared to the power of 11 over 11 plus some constant. Should be this guy. And you could check. I mean, now we probably should, like, distribute that, but I mean, we could check, but you would check by taking the derivative, right? You take the derivative, you should get back to the original guy that you have at the top. Let's see. Oh, wait a minute. Nope. I just realized something, right? That's our u du. Oh, we didn't put it back, did we? I think I put the wrong thing. Let's back up. Right here. This guy. For some reason I wrote du. I need to put back u, right? U is, I was like, yeah, because I was doing a quick check in my mind. I was like, wait a minute, this is not matching up. X cubed plus, hey. That little bird or squirrel, you're gonna have to forget it because I'm not letting you out. Stop. No. Thank you. No, get down. Get down. She sees something out the window, so she just, like, she just want to get to it, but she can't. Even if I let her out, she's not gonna catch it. They always scurry off or run away, right? We were supposed to put the u back, right? And I think it's a power of 11. Okay. So now the 11s cancel. We get our power of 10. We have our proper u, and we get our du, right? Okay, that feels better. And you see the result here. Okay. So again, this is now prior to today, something like this, you might be tempted to try to expand this. Obviously, you're not going to expand the power of 10, right? You could, but that's not reasonable, right? And so if you try to expand this out and use techniques that we've done before, again, that's not reasonable. So this is where you would use substitution. Okay. Let's see if we can get another one. Kind of breezing through these. We're asked to evaluate this. Let's see if we can do a substitution, right? So maybe we can let u, it looks like maybe if we let u be what? 1 plus x squared. If that's our u, then our du is going to be what? 2x dx. All right, notice we have the 2x dx on top, right? So that's a good omen. So now the original, this 1 plus x squared under 2x dx, the integral of that, we can rewrite it as, it looks like we have u on bottom, du on top, and we're taking the integral. So du by u, the integral of that is what? The natural log, ln u, plus some constant. So then that's going to be the natural log of 1 plus x squared plus some constant. So then it becomes 2x dx over that. Right, I think we're good to go. Natural log of 1 plus x squared plus a constant. Okay. So we've seen a few examples. I kind of hesitated initially because we were taking a derivative. I was like, are we already introducing integration by parts? I was like, no, it's not time for that. And then once we kind of got going through a few examples, I was like, oh, okay, I see what they were doing. They were priming us so that we can successfully do this step here, right? Once we identify our u and then correctly writing our du, right? So this is the key with the substitution, and then you make your substitution, do your integration, and then you reverse the substitution. Okay. Okay, let's give this one a go, right? This is similar to what we just did, but there's a nuance, right? So if we let u be, let's do the 1 plus x squared, okay? Notice that our du is what? 2x dx, all right? So then the original can be rewritten as what? U squared under du, right? That's not the same as du by u, right? So I'm going to rewrite this. I'm going to rewrite this as u to the negative 2 du, right? If it were a negative 1, it would be natural log, but in this form, it's not ln, right? So then now we add 1, it's going to be what? Basically negative 1 over u, right? U to the negative 1 over negative 1. I rewrote it as this guy. plus some constant. When we make a substitution back, one plus x squared, -1 plus a constant, right? And you see it here. Okay. So we have this quick check. All right, let's give this one a go. So now, again, the trick is finding a proper U. Okay. So I'm tempted to do, let's start here. Let's let U be, let's let it be 3x. If U was 3x, that means our du would be what? 3 dx. We have the dx, we don't have the 3. Let me see. So a third, how do we, give me a second. Let me think about it for a moment. What's the derivative of natural log? 1 over x. Okay, so I'm not filling this u, right? So I'm going to get rid of this guy and I'm going to choose a different u, right? Because it's not really panning out. So now I'm going to say, okay, well, let's let u be, let's let it be the natural log of 3x, okay? So then maybe our du could be, what's the derivative of that? It's going to be what? 1 over x. So then 3 over 3x, right? Which is basically just 1 over x. Because again, it should be du over u. So it's going to be 3 over 3x. And then we still need our dx, right? Notice we have our dx over x. We have our natural log of 3. This is a much better substitution, right? Okay, I feel good about this. Sorry. Stop. Okay. So now if we make our substitution, the original becomes, it looks like our u is on top. So it looks like we just have u du. U du, and we're integrating this, right? So the integral of u is going to be what? U squared over 2 plus some constant. And we reverse the substitution. So it's going to be the natural log of 3x squared. I'm just going to write it like this. It's the natural log of 3x quantity squared. Yeah. Over 2, right? I feel like they can cancel. I'm really tempted to like bring this guy down, cancel the 2's. But my hesitation comes because usually the power is like on this guy, on the u, right? If it were on the u, then yes. But in that position, I'm not convinced. So I feel like this is the safer route. I'm just going to leave it like this because of what I said a moment ago, right? Plus some constant. So I'm going to go with this. What might happen, they might bring this down, but I don't think that's going to happen. Again, if that 2 were like here, then yes, no thoughts, right? It comes down, they cancel, you're good to go. But in that position, I feel like we need to leave it. All right, I think that this is the better result. Okay. So when we look at it, and you see it here, natural log of 3x squared over 2 plus a constant. That's why I was hesitating. I was like, can we bring that down? I was like, it's not usually there, when we do that, right? Notice it did this. Now, originally, we tried to do the 3x and it wasn't panning out. Things weren't matching up, it wasn't being clean, right? So I was like, I had to call an audible and try a different U, right? So then we tried this U, it worked out, everything matched, and then transformed into this guy, and we finished with the same result. Okay, give me just a moment. Go ahead.
How is u equal to the natural log of 3x and du equal 1 over x dx?
Okay, so u equal to natural log of 3x is just something we chose. The goal is, the thing with substitution is we're trying to find a u so that when we find du, those components are here, right? So originally we tried to let u be 3x. So that made our du was what, just 3? But it wasn't matching up, right? When we did that, it wasn't matching. We were going to have the natural log of u. We had an extra 3 in there, right? So we couldn't substitute all the necessary parts. So then that, to me, that was a signal. I was like, okay, well, maybe we have the wrong u. So let's try a different u. So then we just chose, okay, we were like, okay, well, let u be natural log of 3x. Remember, so the derivative of natural log is du by u, right? So that this derivative of this guy is going to be 3 over 3x, which simplifies down to 1 over x dx. All right, 1 over x. Go ahead. So then we got our natural log of 3x, right? So that gets replaced by u. We have our dx over x. That gets replaced by du, and it looks like this. All right? So then from here, the integral of u is u squared over 2 plus a constant, and then you reverse the substitution. So substitution techniques, it takes some practice and exposure to kind of get used to it. Really, I'm really just trying to use this to expose you to the technique so you're at least aware of it. So as you're trying these different integrations, if one thing doesn't work, then maybe try substitution. If substitution doesn't work, we have a few other techniques that we're going to introduce to next class. Right now, we're just focused on substitution. But yeah, you just try something that it doesn't work, you try something else, right? We have this whole list of like different techniques that we can do. So I'm just kind of bringing these techniques to your attention for you to practice on your own. Okay, guys? Okay. All right, let's keep going. Hopefully that answered the question and cleared it up on some level. Okay, let's try this one. Okay. So off the rip, right? I'm tempted to let my u be x squared. If my u was x squared, then my du would be what, 2x dx? But notice we have an extra 2 in there. We want the substitution to max. This guy should be somewhere in the mix over here, right? We got the x dx, right? X dx, but we have an extra 2. So what we need to do is move that 2 to the other side. So the du, we're going to say half of du equals x dx, right? So now let's do our substitution. So the first, we started with x e to the x squared dx, okay? So now, e to the x squared is, we're going to rewrite that as e to the u. Now, this x dx right here is actually half a du, right? So we're just going to introduce the 1/2 du. We're going to integrate this guy, okay? Because I started to use this technique on the previous example, but it still wasn't panning out. So that's why I was kind of like flustered a little bit, right? So when we go to integrate this, the half we can actually just move it to the front and kind of ignore it until the end, right? So this is actually the same as 1/2 times the integral of e to the u du. The integral of e to the u is itself. So this is going to be 1/2 e to the u plus a constant, right? And again, you can check really quickly, the derivative of e is itself times du, right? All right. So I think we're good. But yeah, we get our half, right? So then we need to reverse the substitution. Let's see. So this is going to be 1/2 e to the, our u is x squared. We might write this as 2x. Yeah, I'm just going to implement what we did on the previous example. I think we're okay. This should be the same as 1/2 e to the 2x plus a constant. And again, if we take the derivative, the constant is gone. The derivative, see, my only thing is, I mean, it's just the way you write it. Maybe they might leave it as e to the x squared. Let me see. That's the only thing I'm not sure on why they did it in the other example. But it's fine. It does mean the same thing. I think it's maybe prerogative or something like that. But it's fine. All right, I think everything else we got the same. And the safer thing is, to me, is just to leave it like this. And the reason I did that is because, like, when I went to check by taking a derivative, when I had it as e to the 2x, that doesn't encourage you to write it as e to the x squared, all right? But let me see if that happens in the other example as well. I'm gonna go back real quick. That's a quick check. This one, was it this one? Where is it? Was it this one? Where'd it go? It was one with E, and I thought it was more recent than that. What is this one? No. Where is it? Sorry, guys. This one, right? Oh. Yeah, that's weird. I still probably would have left that. Maybe it's just because we were finding dy and we weren't integrating. Yeah, I'm not sure why that's a 2x. I mean, I get that you can write it like, again, a power to a power. You can still bring that guy down, but why write it this way? Why not leave it like that? Anywho, if something like that comes on an exam, I would just give it to you. I wouldn't, if it's not clear, I wouldn't hold that against you. Okay. All right. Check. We did this one. We did 8. Okay, we're here. Let me check on you guys in Zoom. Let them in. Right here. Okay. Ooh. Okay. All right. So let's see if we can do substitution here, right? So we're going to say let u be what? Let's try x plus 3. So then our du is just what? Dx? Because the derivative of 3 is 0, the derivative of x is 1, and then we have our dx based on what we said earlier, right? So if we do our substitution, the original becomes, it looks like du by u. And this integral, I think, is a natural log of u, ln u plus some constant. And then we just need to put the u back. So that's going to be the natural log of x plus 3 plus a constant. Yeah, that looks good. Okay. Okay, let's see if we can do substitution here. Let's try, let's see, let's let u be x squared plus 3. Our du is going to be what? Oh, is that a typo? Our du will be what? 2x dx? We have the x dx. We could just move the 5 to the front and ignore that. And we need the x dx. So the same thing as before, we need to move the 2. So we're going to have half a du gives us our x dx. Okay. Okay. So now the original is going to become, I'm going to move the 5 in front of the integral. The half we can also move in front. Okay. So now we're gonna have the integral. Actually, we haven't done our substitution yet. So yeah, we're good. We're good. I'm gonna just go ahead and do it anyway. So the half I'm gonna move to the front. Limits of integration. I'm going to ignore the limits for right now because we're going to evaluate it. Well, I don't really want to ignore it, but these pertain to X, right? I should change them in terms of U. I'm just not going to do it right now because we don't need to do that. We just have to be cognizant that 0 to 1 is in terms of X. Okay. Let me think. I think like maybe if you plug in when X is 0, okay, I think I'm going to just do this. We'll make the adjustment or whatever. When X is 0, U is 3. When X is 1, U is 4. Right? I think it's really going from 3 to 4. We'll go with this for right now. The X squared plus 3. So then we're going to have the square root of U. And then the X dx, the half we've accounted for is du right here. Right? So there's a few different parts going on, right? For the sake of simplicity, I know I could just move this 5 in front and it'll preserve the integral. I had this extra 2 here, so when we move to the other side, we got a half. So we got our x dx. You see the x dx right here, right? So then the x dx becomes 1/2 du. The half I put here and the du was here. I think those are all the substitutions, okay? So now we're ready to integrate. I'm going to leave this as 5/2. This is going to become what? U, let me see, 1/2 is going to become what? 3/2 over 3/2 plus some constant. If we flip and multiply, I think it becomes 5/3. All right. So 5 over 3 times u to the power of 3/2 plus a constant. Okay. That's fine. Actually, let's back up. Let me get rid of this because we have our limits of integration. Again, we would evaluate this as u goes from 3 to 4. I feel like that's a little bit extraneous because I'm going to go ahead and substitute back before I evaluate the integral. So if I substitute back, right, when I substitute back, I can go back to my original limits of integration. So that 3 and 4 part, you can skip and ignore that. I'm just doing that just for the sake of being like accurate. So now when we reverse the substitution, the 5/3 persists. U is what? X squared plus 3 to the power of 3/2. But now we want to integrate as X goes from 0 to 1, right? So you really could have ignored the 3 and the 4. I didn't want to write 1 and 0 the whole time, knowing that pertains to X and we're doing everything in terms of U. So I converted the limits to in terms of U. I don't even know if that's all the way proper, but I do know that the 0 and the 1 pertain to X, right? So when I evaluate the definite integral, I need to make sure that everything is in terms of X, okay? So then, if we keep going, when X is 1, what is that, a 4? Square root of 4 is 2, to the power of 3 is 8, times 5 becomes 40 over 3. When X is 0, 9, did I do that right? When X is a 1, that's a 4. Square root of 4 is 2, to the power of 3 is 8, okay. When X is 0, we get what, 3? That's not a perfect square. Okay. So it's going to be what, 3 times the square root of 3? So if that by itself is 3 times the square root of 3, the 3's cancel, you're going to have 5 times the square root of 3. So we're going to say minus 5 times the square root of 3. That's about it. Or that happened to be a perfect square. And then I would just use the calculator from there. Let me go ahead and use the calculator just to. Okay, let's reload and refresh. Okay. I kind of want to do something. So I'm going to go to my y equals. I want to put in 5/3 parentheses x squared plus 3. Close parentheses to the power of 3/2. Okay. Then I just want to compare. Like, did I do my calculations right? I'm going to do it twice, right? So first I'm going to do my 40/3 minus 5 times the square root of 3. We get this result. Then what I want to do is call on that function. I want to evaluate that function when x is 1. I'm going to say minus that same function when x is 0, and we should get the same decimal. Okay. That's what I was just trying to check to make sure that they matched. So then we could say approximately 4.67. Okay, let's see. How do we do? Yada, yada, yada. Okay, so our u was x squared plus 3. Our du was 2x dx. So then you see the half. Okay. All right. Where is it? Okay. 2. Where did they get the 5/2 from? Here it is. U to the 1/2 du, 5/2. You see it here. I think we had this. So then you see the flip and multiply. So you get the 5/3 x squared. Okay. Plus 3 to the 3/2 plus a constant. And then now they have the 1 to 0, right? And 4.673. I think we got that guy. All right. Notice the C's cancel. 4.673. That's what we got. Okay. Okay.
Professor,
Yes.
where did they get the 5/2 from again?
Okay, let's go back. Right here, right? So if we're trying to get to the 5/2, right? So we let our u be x squared plus 3. So from there, that means our du was what? 2x dx. But notice there's no 2 here, right? So from here, we had to divide both sides by 2, and that's where this comes from. So we've captured the x dx. You can see the x dx here. The 5 we just moved to the front. And then when we substitute the x dx, we had to introduce the 1/2. So with this 5 being in front and us introducing the 1/2, that's where the 5/2 comes from. Or this 5/2 here. That's where it comes from. Okay. We probably could have done without the 4 and the 3, right? You can just ignore that. But then, once you reverse the substitution, you got to be sure to do the 1 to 0. Okay, so we have a solid 30 minutes. I do want to take this time to go through as much homework as possible. If anybody wants to work on like other sections, we can, or we can just focus on this one. I'm just going to start doing questions from this section, but if you guys want to work on another section, just stop me and we can. Let me see. I'm going to go ahead and pull this up. Let's go full screen. Get rid of all of this, to be honest. Close these tabs. I'm going to start here. You can block for now. Sign in. Allow. This. This is calculus, okay. Wow, yeah, that's fine. And we're pretty much at the end, way down here. So yeah, week 12. So I want to say week 13 is exam 2. I mean, yeah, it should become available this Sunday, right? So let's work on 4-5, integration techniques and substitution. We got what, 27 questions, so we'll do as many as we can. And I want to just get straight to section 4.5. I don't want to do like a previous section. So we're gonna have to skip this for right now. That's augmented review. That's 3.9. We're on section 4.5. 4.5 starts on question 8. So be sure to check by differentiating. Evaluate this integral. Okay. If we let our u be that, then our du. All right, let's take some notes here. I was kind of pausing to see, well, maybe we can do it quickly, but I was like, we need to take some notes. Okay, we're gonna take it from there to here, here. Okay, I want to just copy and delete. Okay. Add a page, and let's go seamless. Right there. Let's paste. Are you at the top? Why do you always do that? Let's cut. Back to where we were. Way down here. You can do it. I believe in you. Come on. All right, I'm gonna have to reboot this. Wait, are you back? No? Okay, it rebooted itself. Come on, right here. We want to add a page. Okay. Can we just paste right here? There we go. Okay, let's go to view, seamless, awesome sauce. Cool, that's right. Okay. All right, that's decent. I'm gonna work right here. Okay. Okay, let's try substitution. I'm gonna put my charger back. I think it'll work. Okay. So now, again, the trick is to find the proper u. So we're gonna say, let u be what? 6 plus x to the 7. So that means our du, 7x to the power 6 dx, right? Notice we have our 7x to the 6 dx, 7x to the 6 dx. So that means we're on the right track, right? So now let's do our substitution. So the original is going to become what? The integral of u to the power of 4 du. So then now when we integrate, it's going to become u to the power of 5 over 5 plus some constant, and we reverse the substitution. 6 plus x to the 7 to the power of 5 over 5 plus some constant. Okay. I feel good about this. I'm gonna go with it. Use parentheses. Okay. So we got this 6 plus x to the power of 7 and to the power of 5, right? Was it over 5 like this? What's the constant? That was it. Okay, let's do another one. All right, let's just get a screenshot. Just gonna take it from here to here, like this. Same kind of deal, right? So we're just gonna copy and delete. Over here on a new page so much. I appreciate that. you gotta be kind to your equipment, you know, energetically. It seems like it picks up the minute you start like calling it stupid, it responds to that and it starts acting stupid. you get what you expect. Right? If you expect it to be stupid, you can't be surprised when it acts stupid, right? It's the same thing in life. Okay, so let's see. Let's let u be what? 5t cubed minus 8. So then our du, the 3 comes down. What is that? 15 t squared dx or dt. So we got our t squared dt. We don't have the 15, so we need to move the 15 to the other side. So then we get 1 over 15 du equals t squared dt, right? We got the t squared dt, t squared dt, right? So now we're ready for our substitution. So the original becomes, it's going to be 1 over 15 times the integral of, it looks like it's just u du. All right, so then that becomes 1 over 15 times what? U squared over 2 plus some constant. So then when we substitute back, we're going to get our 5t cubed minus 8 over 30 plus some constant. Okay. Oh. All right. 5t cubed minus 8 over 30 plus a constant. 5, 8, 30. Okay, let me zoom out some. Determine the change of variable. So we let u be 5t cubed minus 8. So that's d. Check. Okay. In terms of u, so it was 1 over 15 times u. So 1 over 15, no. I don't know what all that is. We got some kind of lock on somewhere. Oh, come on. What is that? Okay, I don't know. It was just bugging out. 1 over 15. Nope, that's nope. Back up. 1 over 15 u. Right. I think that was it there. Okay. So we said what? 5, 8, 30. Okay, so it was like I think it was 5t to the power of 3 minus 8 over 30 plus some constant. I think that was it. Oh, did we forget? 2, right? I think we're getting the squared power of 2. And I think we had it written down, I just forgot. Oh, I forgot to write it as well. That's all right. So right here, squared. Okay, let's go on to the next one. Okay. So if we let our u, I guess we should just write it out. I keep trying to not write it, knowing good and well I should just write it. Trying to do it in our head is going to make it way worse, right? Versus if we write it out and look at it written all the way out, then it makes it much easier to see and visualize and get a sense of what's going on, right? Let's copy and delete. Right here, we'd like to paste, expand, like that, all right? Okay, check by differentiating, okay? Got let's hang out for like 10 more minutes at least. So let's let our u, I'm thinking 9 plus 5x. So then that makes our du, that's gone, just what, 5dx? Right? Notice here, we have our 5 times dx. Okay, so then when we go to do our substitution, looks like we get du over u, which is what, natural log of u plus some constant. And then you reverse the substitution, natural log of 9 plus 5x plus some constant. All right, 9 plus 5x plus a constant. Oh, absolute value? Okay, that's fine. So the reason it's absolute value, because again, if you were on an exam and you put parentheses, I would just give you credit for it. But the reason it's absolute value is because they didn't force the x to be strictly positive. Generally speaking, the x is strictly positive. They just didn't force it here, so we just need to do absolute value, so that way, we're not working with like things outside our domain, right? Okay, let's keep going. All right, let's do the same thing here. Let's get a copy, take some notes. And again, all the stuff you see me writing, you know how it goes. I'm going to make a copy available for you all at the end of class before we go separate ways. So you can at least reference these materials and pull it at your leisure. Okay, I do need to do some housekeeping on my channel. I have not been loading this stuff into the playlist. It's on the channel, like these recordings are live stream. It's just not organized. I need to do a lot of work. I need to create a logo, an intro, an outro, and I just been avoiding it. I could pay somebody, I just don't want to pay them either. I don't mind doing it. I just been lazy. And I do kind of want to like start making shorts, and I don't know how to do all of that stuff. I just been lazy. Because like again, when I'm not with you guys, I'm either driving like Uber and like Uber Eats and crap like that, or I'm gaming or sleeping or just hanging out with folks, right? So, but I do need to do some housekeeping. Let's see. Be sure to check by differentiating. Okay. So I'm thinking, notice here they force x to be positive. Let's let our u be the natural log of x. If that's our u, then our du is going to be what? Dx by x. All right. Notice we have our dx over x. All right. So now when we go to do our substitution, this is going to become what? U to the power of 12 du. Okay. So then this is going to become u to the 13 over 13 plus some constant. And that's going to become the natural log of x to the power of 13 over 13 plus some constant. Okay. Because they force x to be positive, we don't need the absolute value in this case. So we should be Gucci. Okay. Right here. Okay. Let's go like this. Cool. We're gonna say parentheses ln x to the power of, what do we say, 13 over 13 plus some constant. Okay. All right. I feel like my heart skips a beat every time I submit. And then it's like, I'll be like in anticipation, holding my breath. And then when it's wrong, I'm like, ah. And then when it's right, I'm like, ah, I can breathe again. But it's okay. I mean, it's kind of like a little game. It's a puzzle, and it's like your ability to pick up on the pattern and apply what we've been talking about, right? I try to make the experience as light as possible, because I do acknowledge that, you know, it is intense, especially if you're trying to learn it. And I do acknowledge that some of the content is intense, right? So because of that, because it's a remote nature, you know, because of just the design, you know, that's why, again, I know I've said this before, but I do the unlimited attempts, a minimal late penalty. You can access stuff all the way up until the end of the semester. I try to make it as light as possible within the confines of, you know, whatever restrictions or parameters that I have to abide by. You know what I mean? Hopefully it works for you guys. I do acknowledge it's intense, you know, and I just try to encourage you. I don't really know how to make it lighter. I mean, there are ways, but you know, it's kind of what we have to do for now. Okay. But I think I want to, let me see if that's my U. Nope. If that's my U, my DU. Okay. So I'm tempted to let my U be, I probably should write it out before I submit it. But see, if my U is, I started to do, my U was e to the x to the 28, but then my DU was generating another e, and I didn't want that extra e. So instead of letting my U be e to the x to the 28, I think my U is just going to be x to the 28 without the e. So I think it's just going to be b. Then our DU would be what? 28x to the 27. So we would have to multiply by 1 over 28 when we're going to find our DU. Okay. In terms of U, so we're going to have, we have our 1 over 28 times our U, e to the power of U. DU. All right, I think that was it. And if I need to write this one out, just let me know, Cam. So then we go to take the integral. The integral of e to the U is itself. So it should just be e. It should be 1 over 28. See, so I'm gonna hit fraction. It should be e. No. Yeah, e to the U. So e to the power of x to the power of 28 over, I think we had to introduce a 1 over 28. So over 28 plus some c. Let me try to do a check before I submit this. Now, when I go to take the derivative, the e to the x to the 28 is going to persist. Then we're going to say times the derivative of the power. So that's going to be times 28x to the 27. The 28's cancel. We're left with just the x to the 27. We're good to go. All right, I'm going to submit this. Okay. Again, if I need to write it out, just let me know. I can. Let's hang out for like 5 more minutes. Let's try to get as much done in 5 minutes as we can. Let me see if my U, did we do one like this? I'm gonna just go ahead and take some notes here. That's the simple take notes. All right. So let's get this from here to here, like this. Boom, shakalaka. Let's copy and delete. Hop over to our notepad and let's take some notes here. I'm just gonna paste. Cool. Okay. So now let's see. Let's let U be, we're gonna do this 4 minus 5x. So then our du would be what? That's gone. Look like it's -5 dx. We have the dx, the -5 is extra. So we're going to move it to the other side. So then we're going to have a -1/5 du equals dx, right? Dx matches dx, right? So now when we go to do our substitution, the original is going to become, we got this -1/5. I'm just putting it out in front for the sake of simplicity. It looks like it's du over u. All right, so that's natural log. So then that's going to be a -1/5 times the natural log of u. Okay, notice we don't have anything that says x is strictly positive. So we're going to force the absolute value plus some constant. Okay. And then if we reverse the substitution, -1/5 times the natural log of u, which is 4 minus 5x, absolute value. So like this, and plus some constant. Okay. We'll do one more after this and then we'll call it a day. Let's see, how do we do? We got a -1/5 times the natural log of the absolute value of 4 minus 5x plus some constant. Let's make that a capital C. Okay. Okay. This will be the last one. Here, here, here. Okay, let's copy and delete. I'll drop it right. Sure. Paste. Awesome sauce. All right. Okay, so we're gonna let u be, we have this x to the 9 plus x to the 7 minus x to the 5, right? If that's our u, then our du is gonna be 9x to the 8 plus 7x to the 6 minus 5x to the 4 dx. Okay, and I think it matches, right? You see it here. Okay, so this looks like it's really just the integral of u to the power of 6 du. So the original becomes u to the power of 6 du. That becomes u to the 7/7 plus some constant. So then that's x to the 9 plus x to the 7 minus x to the 5th to the power of 7/7 plus c. Okay. So I feel like it's not too terribly bad. It's a little bit, you do kind of have to take your time a little bit and be neat and organized. Notice I'm giving myself plenty of space, minimizing my clutter as much as possible. I'm just trying to be organized, okay? Right here. Okay, like this. So we have that u, which is, I think it's x to the power of 9 plus x to the power of 7 minus x to the power of 5, all to the power of 7/7. Nope, that's not a 7, plus some constant. All right, gentlemen, would you guys like to ask any other questions before we go our separate ways?
Professor,
Yes.
I just have like only 3 questions from like a previous section. I think it was 3 point. 6.
Can you resend the emails? Like just resend them, or click the ask my instructor and we'll do it that way.
Yes.
Okay. All right, gentlemen. So we're going to go ahead and officially end this session here. You're more than welcome to hang out. We are going to work through, like, it sounds like at least like 3 examples. All right, so we're going to kind of work through that. But if you have to go, you're more than welcome to go. And from one beautiful mind to another, enjoy the rest of your evening, guys. Okay. We're just going to kind of hang tight and work through a few more examples. But again, you don't have to stay. Like, if you need to go, I'll see you next time. Oh, did you die? You died. Okay. Let's try to revive you.
I sent them.
Morehouse. I'm just trying to get my phone like a minute or two to power back on so I can like check these there. Okay. Let's log in.
I sent them to you, Professor.
Yeah, I got it. It's my device was, I had to charge it.
Oh, okay.
Okay, that worked okay. I know. It's not reliable. You can't rely on it. Okay, let's see. Okay. So pulling up the first one. The first one looks like it comes from section 3.6 marginals. Let's see what's going on here. Okay, let's pull it up here. Come on. Right here. Okay. So it says the average cost for a company to produce X units of a product is given by this. Use a prime to estimate the change in the average cost as a product goes from 100 to 101 units. Okay, average cost. So then A prime. The rate of change to increase it by 1, right? So I think all that we do is take the derivative and evaluate it when X is, I think, 101. That should be the average cost to produce the 101st item. The rate of change to produce the 101st item, right? It looks like we had to use the quotient rule. You can either use the quotient rule. Let's just do the quotient rule. I think I could take my notes here. Let me see. So if we say the bottom, which is this, times the derivative of the top, which is going to be what, 16? So it's going to be, so that's the bottom times the derivative of the top minus the top, which is this. Bottom times the derivative of the top minus the top times the derivative of the bottom, which is a 1 over the bottom squared. Okay. So if you simplify this, it looks like those 16s cancel and we're left with just negative 200 on top. Then I think you just plug in when x is 101. Let's see, if that doesn't work, we'll adjust. Reload and refresh. Okay. So then let's do negative 200 divided by, I'm gonna say 101 squared. I think that's it. It doesn't say anything about rounding. So about, they lose 2 cents to produce the 101st item, or the cost is reduced, is going down by 2 cents. So let's say a negative 2 cents. Negative 0.02. I think that's right. Right. So again, to kind of recap with that one, again, it says use A prime to estimate the change in the average cost as production goes from 100 units to 101 units, right? So they gave us the average cost function. The derivative is going to tell us the change in the average cost. And then all we do is plug in, after we find the derivative, we plug in x equals 101, and that'll tell us the change in the average cost of that 101st item to go from 100 units to 101 units. And so it should cost us 2 cents less to produce an additional item. Okay. So hopefully that one was okay. Let's pull up the next one.
Okay.
Go ahead.
No, I said
Okay.
I'm okay.
I think you said you're okay. It was still kind of choppy, but I'm going to pull up the next one. Okay, let's look at this one. So I'm going to drop it right here. I really off feature. Oh, okay. Let me close this. You can just, there you go. Awesome. Let's try that one more again. Yes, that's exactly what I want. Okay. So the next one is this guy. Okay, this comes from section 3.6, marginals, differentials, and linearization. Okay, it says use the graph on the right to answer the following question. Alan earns $230,000 per year and is considering a second job that will earn him another $20,000 annually. At what rate will his tax liability, the amount he must pay in taxes, change if he takes an extra job? Express your answers and, okay, rate of change, right? Mm-hmm. Another 20,000. 200. Okay. So at 230, right? So 200, 250, so that's 225. It looks like it's the same. His marginal rate looks like, what is it, like 36%, right? It seems like it's just making an ordered pair. We just got to find the slope. If he earns another, the slope was like a 0, right? Because it's a flat line. If we look at going from 230 to 250, it's a flat line. So his tax liability will change. It shouldn't change his liability. His tax liability would change by about $0 per dollar earned. I think that's 0. I'm going to try 0. It's given the average marginal tax increase and marginal taxes increased income. The marginal tax gives percent per dollar change by about $0. 40. It's not changing there. 250. That slope is 0. What am I missing? Tax rate. It looks like it's 36%. Maybe. Tax dollars paid per dollar earned. 36%. Maybe they want the 36% of his total income. 250. %. Let me try this, and then if I don't get it, we'll look it up. I think we can do the 30. I think it's 36. I'm gonna say 36% of 250, and I think that might do it. If that doesn't do it, then we'll look it up. Per dollar earned, his tax liability would change by about 90. I'm not confident in that. I'm just going to go ahead and look it up. I'm going to go to review an example. So let's see. In this one, 250, another 50 will take it to 300. So notice that the 250 and the 300 are the same, right? So this one is similar, which is 36, right? So 36% of 300, whatever that is, right? So I'm anticipating 108,000. Give him average and his current income and the marginal tax rate. Wait, it says the change in his liability is given by an average of the marginal tax rate, his current income, and the marginal tax rate, his increased income. Well, the average should still be the same, 36. Notice the average rate for his current is about 36%, right? Is also 36%. Notice that looking at the graph remains constant. So therefore his average should be 36%, right? Marginal tax percent per dollar change. That's the rate at which it's changed. Second job is about 36 cents for each dollar earned. So 36%. So that's we got the concept correct. We just wrote the answer in the wrong format, right? So we get that it's not changing. So then 36% is going to be 36 cents per dollar, right? So I think it's the same. We get the same result. So 36 cents per dollar right here. So 0.36 per dollar. Okay. All right. So that was more formatting. Again, the way we were thinking was fine because the rate didn't change. It was a flat horizontal line. We were just writing the final answer in the wrong format there, right? That's what was going on there. Okay, hopefully that one wasn't too terribly bad. But see, that's how it goes. Like you do what you can on your own, and then once you hit that wall or whatever, you click on the view and example. Most of the questions have view and example. They all don't have it, but that's usually the view and example. I would say at least 90% of the questions have it. And I want to say it gives enough detail to where, you can get what you need to get out of it. Let me pull up this other question. And again, if you have questions on this, we can talk about it. Let me get rid of this.
So you said there was 36% because it was like a flat.
So, okay, here, let me pick it back off of this one. If I go to the view and example, right? So this one, it says that he earns 250,000 per year, and then he wants to do a second job that's going to earn him an additional 50,000 per year. So he's going from 250 to 300. But if you look at the chart at 250, that rate is about 36%. 300 is also about 36%, right? So the average of those two is still going to be 36%, right? So then his marginal tax rate is going to be 30%, 36% of each dollar earned. So 36% of a dollar is 36 cents, right? Because basically, you know, the first one is 36%, the second one is 36%. The average of those two is still going to be 36%. So then you just have to write that in terms of dollars per earned. So it's 36 cents per dollar earned. Does that make sense?
Yeah. Okay. Yeah.
Yeah. Because they were both 36. So the average of 36 is itself. The average of them both being 36 was itself. I think I got rid of that. So let's go ahead and drop this here. Okay. All right. I think so. This is the third in the set of three. It comes from section 3.6, question 55. It says a painting firm contracts to paint the exterior of a larger water tank in the shape of a half dome, a hemisphere. The radius of the tank is measured to be 130 feet with a tolerance of plus or minus 6 inches or plus or minus half a foot. The formula for the surface area of a hemisphere is that use 3.14 as an approximation for pi. Each can of paint costs $40 and covers 300 square feet. Calculate the derivative of the area, the approximate difference in the surface area due to the tolerance. So dA, right? The differential with respect to A. Okay. I mean, yeah. Surface area due to the tolerance. Surface area of hemisphere. Assuming the painters, so we want the area in terms of what? The radius? Okay. Each can of paint costs $40 and covers let's see, are we? So let me see, the radius of the tank is measured to be this with a tolerance of plus or minus inches. What is this in terms of feet? So half a foot. So then, you know,
If that's what you're talking about.
I'm still, go ahead. I'm still kind of thinking about it. Give me just a moment. I'm still thinking about it.
Okay.
Because I'm tempted to like plug in those tolerance, but I think they want me to take the derivative. I'm just gonna click on the view an example real quick, just to get it started. So yeah, they did take the derivative, right? Okay. So when we take the derivative here, the 2 comes down. Simplify your answer. So 4 pi r feet. Let me think about that. Feet squared, right? Okay. Let's try 4 pi r. I'm gonna say feet squared. Your second answer is correct with your first answer. Why is that off? Do they want us to use 3.14? They probably want us to use 3.14. Nope. Here. Nope. Let's use 3.14. See if that makes a difference. No. Okay. Reload and refresh. So we're just going to say 4 times 3.14. Nope. Try that again. 4 times 3.14. Okay. This. So let's do 12.56 R. Feet squared. Okay, let me see. Oh, dr. Yeah, we forgot the dr, right? Let me just do the viewing example so we're not having to come back. Yeah, we need the dr, 4 pi dr, right? Okay, yeah, we were just missing the dr. So then right here, we can still do the 4 pi r dr because it's a differential. Okay, I think that's what we're missing. We just got it wrong across the board. They plugged in the radius as well. Okay, I'm gonna try that again. The tolerance. Okay, let's at least generate that number here. Let's I'm gonna just let me make sure I can generate that number, right? So if we say that times the 130, feet squared 4 pi r 816. Feet plus or minus half a foot. Why is that not 130? Okay, let me see what's going on here. For an example, yeah, we got that. That's fine. Oh, dr. Maybe we're forgetting the dr. R and dr. Yeah, I think we're forgetting the dr. Let me see if I can think about how to solve for that. Oh, we need the dA plus or minus. All right, that's fine. Well, you should get 2 answers though. Okay. Okay. So we were forgetting the half. Okay, that's fine. So then if we take our result and say times 0.5, okay. Okay, that's not too bad. So yeah, I just wasn't taking it far enough, right? So 4 pi r dr, right? So the dA, normally it would be dA by dr. You take the derivative, so the 2 comes down as 4 pi r, but then we just want the dA, so we got to move the dr to the other side, the differential. So then, they wanted pi was 3.14, r was 130, and the dr was the plus or minus the 0.5 feet. Again, the negative doesn't make sense in the context, so we just take the positive. I'm going to go with this for now. The painter should bring in extra blank cans of paint to cover the extra area. Okay, so if we have 816.4 and each can of paint costs 400 and covers 300, so what, 3 cans? Each can of paint costs $40 and covers 300 square feet. You need a total of 3 cans. Round up to the nearest integer. I'm just going to say 3 cans. That's kind of weird the way they worded that. The painter should plan to spend, so then 3 times that $120. It wasn't too bad. We just had to get past like some of the terminology or the nomenclature there. Was that did your questions get answered with this one?
Where'd you get the 3 from?
Okay, so is the solution for part A okay?
Yes.
Okay, so once we got part A, so the approximate surface area, including the tolerance, we get was notice that's close. That's just shy of 900, right? So if we want to buy enough cans of paint to cover 816, each can of paint covers what, 300 square feet. So then two would be 600, but that's not enough. So then you would need at least 3 cans of paint. 3 cans would get you to 900 square feet. That would cover the 800. And then each can is $40. So 40 times 3 is 120. Is that okay?
Wait, so do you multiply the 3 to the
So
$4?
the $40, right? So the total surface area, including the tolerance, the surface area of the dome was 816.4 square feet. Each can covers 300 square feet. So how many cans of paint do we need to cover the 816? Well, 1 is 300, 2 would be 600, 3 will put us at 900. So 3 is the least amount that we need in order to cover the 816. And then each can of paint costs $40 times 3 cans, gave us a total of $120.
Oh, okay.
Yeah. All right. Okay. All right. Did you have any others that you wanted to go through?
No, not really.
Okay.
Just from this section.
Okay. Well, just kind of keep working. You know how to reach me. We'll reconnect again on Wednesday. All right.
All right.
Let me go ahead and make a copy of these notes available. I know we didn't write too much. I want to share center box. So when this bar finishes loading, you'll get a copy of anything that you saw me writing. And from one beautiful mind to another, enjoy the rest of your evening. Take care. Peace.
All right.